Hi everyone, we're back today and we're moving on with our layout processes. We're going to look today at radial line development. Now we first looked at parallel line and we looked at T's, and elbows was our main focus in those groups. So laying out items like these. Okay, and what we said when we had parallel line, it's right in the name, we need the outside edges, what we refer to as element lines, we need those parallel. We need those to always stay parallel, and I like to think of them as the bends of the part. They always have to be parallel to use parallel line development. And today we're going to start looking at radial line. And radial line, we're thinking of items that radiate back to a common point that we call a radius point. So we're looking at items like this, a cone. Okay, this is just a simple cone, but everything comes up to here. So we don't have parallel bends or element lines anymore. They come to a common point. And the common pieces we'll see on this will be the cones like we just saw, or maybe a pyramid. And those are the most common types of shapes we're going to see in radial line development. It's one of the most limited processes we have. It's one of the simplest as well. Really, cones and pyramids is all we're going to see in that. But any shape, that's what it takes, is the common point where things radiate back to. What the shape of the bottom is doesn't matter. Could be triangular, could be rectangular, square, but everything needs to come back up to here. As well, to make radial line worth using, that needs to be within a reasonable distance. If we were to look at a frustum of a cone, and a frustum is when the top's cut off, so a round taper. If we were to look at this one, the first thing we need to do is find that radius point. In this view, the elevation, we call it the apex. And if we draw that out and we discover that our radius point is maybe 6-8 feet away, maybe it's 20 feet away, maybe it's 30 feet away, and we can't draw it, then we're not going to use radial line. We're going to figure out a different process that we can use for that. So we need a radius point. We need it in a right cone at this point. And what we've learned before is a right cone. The apex point is on center of the base. So we create this right triangle here. So we need a right cone. We have everything going to an apex point or a radius point, and we need that point within a reasonable distance. Okay? So we're going to start with just like our sample here, just our basic cone. Top's not cut off, it's not a frustum, it's got a round shape at the base. And we're going to look at drawing that one and developing the pattern for that. So let me bring my arm over. When I start a cone, and you'll have a project drawing, shop ticket, shop drawing, whatever you want to call it, I always like to start with a baseline and a vertical. And that's going to be my starting spot for my cone. If we start our development off that, you're going to be given a base dimension, you're going to be given a size down here, and you're going to be given a height of some sort. And that's our 2xy that we can work off of our baseline and height here. So I'm going to mark out my size. Let's go here, and I just tick off each end. Okay, a couple of ticks on there, and I mark out my height. There's my height there, and then I'll connect those points. This I find is just the easiest way to establish. Now, with most of our layout, and we started to see it in round elbows, or talk about it at least, There's usually two ways we can go about our layout, and it's drawing it like we're doing here, and there's a mathematical way. A lot of our layout can be accomplished by math. And when we do the calculations and figure out the patterns using math, they're much more accurate. Okay, there's no rounding, there's no errors as far as the drawing itself. The more we draw, the more errors we can have. So with parallel line, with radial line, and when we get to triangulation, we want to think of the math aspects, and we want to know that this might be a quicker way. In some cases it is, but it has some limitations. It's a little bit inaccurate, and that's just the nature of doing things by hand, is we have a nature of inaccuracy. So there's my cone. We're working from elevation view. I could draw the plan view and it would just be a circle up here, but we're going to take some of the shortcuts we learned in parallel line, and I'm going to do a profile down here instead of anything, instead of drawing the whole plan view. So I'm going to start with that. There's lots of shortcuts that you'll learn through your experience, through your training. But it doesn't really take that much longer to do the whole view in this case. And I always suggest that, you know, until you're really comfortable, maybe a third or fourth year apprentice, that you learn the shortcuts, but you don't always use them. You want to always make sure that you know the process. And the most important part is knowing the process. If you can conceptually see why we're doing things in layout and how we can accomplish them, and you get to a point where it doesn't matter the shape, you'll just be able to look at it and figure out how to lay it out. And that's where we're trying to get. And that's where we will get eventually. So I got my profile. I've divided it into 6 equal parts. And I'm going to bring those vertically. Very important that our profile heights, that's the lines in green here, come vertical. Not up to the apex point. What this view is showing us is how much depth the fitting has, how much it's coming towards us out this way. Okay, so if I flip this green up, that shows how it's here. And it shows me at different points actually how far it's sticking out this way. So it has nothing to do with the elevation view. This is a separate view. It's a separate plan view. And what it's showing us is how far it's actually sticking out this way. Right? So if I took that and flipped it up, it's different lengths at each point because it starts curving, hits its peak point here, and then goes back in. Okay, so really important vertically, always vertically from the profile heights. Once we have them to the baseline, and again, it's always the baseline, so this shape here of the profile never changes. Other things might be added and change inside here, but this view here, our profile view, never changes. I'm going to bring these all up now that I have them to the baseline. I'm going to bring them to the apex point. Now we can start to see, just looking at our part, we know it's a right cone. It's on center. We have our apex point. And like I was referring to there, our profile heights are showing us the depth of the fitting. And when we look at our sample, and we imagine here's our sample, right? Look at the blue line. The blue line is representing the very outside edge, like right up the edge here. And it is the line in the elevation view that we refer to as true length. The blue is truly what we see there. All the purple lines are coming out this way. So they're all got depth towards us this way. And when we look at those lines, the length of them actually gets skewed by the view that we see them in. So if we look straight on this one, because we know the base is straight and it's just a simple cone, all the lines in here are the exact same length. Right? All these element lines, everything that bend along here would be the exact same length. But when we look at this, specifically all the ones in front here that I've drawn in purple, and the center one is the easiest to look at because it's the shortest. The purple line here on center, it looks shorter than the blue in this view, but it's not. The line is leaning out. The line is coming towards us like that. But when we look at it straight on, it doesn't show us the length of it. When I show you my ruler like that, it doesn't look like it's 3 feet long. It looks like the height that you see here. The element lines in a cone are the same idea. They get skewed by the view that we're looking at. But the two outsides are always true lengths in any elevation view of a cone. So the blue lines here are true length. Now I'll jot some numbers on here just to work on that process. So it's always a good idea to label. And remember, everything round, we're going to use numbers. If it's square or rectangular, we'll use letters. So now I know I got my profile view, I got my heights, I got all my element lines in. I know that the two outside edges are true length in the elevation view. And I know that all the purple ones don't look like the same length as the blue, but I know that they truly are the same length. So now let's create our pattern. And because I know that every line is the same length, in reality, I'm going to pick up one of them. Now with radial line, it's one thing. I could swing this right, I could swing an arc right off of here and make the pattern, but I may run out of room. So let me just pull that aside. And I'm just going to give myself a radius point here. So again, I'll pick up the outside edge and I'm going to swing that arc. Now I don't know at this point how much of that arc I need. I don't know if the pattern is maybe half or close to half a circle. I don't know if it's almost a full circle. But what we can judge that off or give ourselves a ballpark is how steep the cone is. Okay? One like our sample that's much taller in comparison to the base is going to be a really small. One that's really shallow, like we would see in maybe a rain cap, is going to be a large pattern. So this one might look something like that. And our sample might look something like that. So, but at this case, we don't know. We have to just ballpark it. This one's fairly steep, so I'm guessing it's going to be closer to this than this, but we don't really know. So let me grab a new pen here. Now, two things with radial line, two main rules. We take an elevation view and we take the true length of the outside edge. We take the blue line and we swing that arc. Okay? That's rule one. The second rule is we now need to make the length of this arc equal to the circumference of the base. So we have to go the distance 1 to 7 and then around again, because we know that the arc length has to be the circumference here. And that's what makes it a cone, is we have an arc that doesn't necessarily equal the circumference that circle or radius is based off of. It has to be smaller, or else it would just be a flat disc. Once we cut something out of it, we shrink the circumference and pull it in. That's what makes it a cone. Okay, so starting point, it doesn't matter where it is, arbitrary, just somewhere at the start of your arc. And I'll put my ruler up and I'll just draw a start in line. Again, there's lots of different ways to measure this length. We could pi times diameter to find it, and we could use a circumference ruler and bend it around that arc and actually measure it. We could put a piece of string there. Anything that we could measure on a curve like that is a totally acceptable way to do it. What we commonly do is take our step off, and our step off is one of our 12 divisions. They're all exactly the same, so it doesn't matter which one I pick up. I'm going to step it off 12 times. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. We get our end point, and now we just join it back in. Take it back into the radius point of the arc, and mine's pretty close to 180. So this is my pattern. Okay? We swing the blue line, the outside edge, we call that the slant height. Okay, the slant height is the outside edge. And it's not, remember that one doesn't have depth to it, so we have to get it all the way to the outside. We swing the slant height. We make the distance of that arc equal to the circumference of the base. And there's our pattern. Radial line development for a cone.